Good day. My name is Chiboze, a graduate student at Notre Dame, and I'm here to present this research on the sensitivity of hurricane intensity to spatial heterogeneities in sea surface temperature. High-resolution satellite imagery of Hurricane Irma in 2017 basically shows the typical features of a hurricane as a synoptic scale aggregate of convective clouds and thunderstorm being stirred by a background flow, in this case, the Coriolis force. Now, various theories have been postulated for the intensification of a hurricane, one of which is the Wishy theory by Kerry Manuel, which viewed the hurricane as a Carnot heat engine, acquiring its energy at the surface through latent heating and losing it at the top of the tropopause. One assumption in the Wishy theory of Kerry Manuel is the representation of surface processes using bulk aerodynamic formulas, giving rise to the maximum potential intensity of hurricanes. However, the sea surface temperature is far from homogeneous. High-resolution satellite imagery from NASA's MODIS basically shows the existence of these filament-type structures and warm and cold core eddies typically seen in the Gulf Stream. Previous research have shown the size ranges and lifespan of these eddies and shown that they range from a size of 30 kilometers to about 160 kilometers and have a lifespan of up to 40 to 50 weeks. Here's another satellite imagery from NASA's MODIS again, showing the existence of these filament-type structures and eddy-type structures in the Gulf Stream. Now, previous work have investigated the influence of SST anomalies on the eye and eye wall structure of a hurricane and how it affects the intensification process. Our research presented here aims to improve the representation of SST anomalies in the hurricane boundary layer using a novel framework that accounts for the realistic sizes, spatial and temporal evolution of eddies and filament-type structures, characteristics of the high wind hurricane boundary layer. We also aim to understand how the interaction between different storm sizes and these mesoscale to submesoscale features, particularly in the eye and eye wall region, modulate the onset of the period of rapid intensification. To do this, we're going to be using the following methodology. Realistic SST inputs from satellite and observation data, particularly in this case from the NASA's MODIS, will be used as the initial data source for our SST analysis. From this, the first and second order moment is extracted. Now, in addition to the first and second order moment, we are also going to be extracting the structure function. The structure function or the variogram is a critical aspect of our workflow because it gives us a length scale of spatial coherence, characteristics of these large eddy sizes and filament type structures seen in realistic SST fields. Now, using the first and second order moment in addition to the structure function, we'll be generating random fields with specified length scales of spatial coherence, which will serve as boundary conditions for our uncoupled model run to investigate the response of different sizes of storms to the presence of these different structure sizes. Now, the initial SST field, as shown in the previous slide, is gotten from the NASA satellite product, which has a horizontal resolution of about 1 kilometer. The time size selected was indicative of the period of rapid intensification of Hurricane Irma in 2017. And the domain side was selected again, just to show when Hurricane Irma passed through a spatial domain of roughly 400 kilometer by 400 kilometer rapid intensification. Now, initial distribution of this domain, of the SST field in this domain, basically shows a Gaussian distribution with a maximum of about 30 degrees Celsius and a minimum of about 27.5 degrees Celsius. A plot of the power spectral density basically shows that most of the power is contained in the larger wavelength or smaller wave number domain. And as we go to smaller and smaller wavelength or larger wave number, we can see a drop in the power spectral density or indicative of the variances. This basically shows that most of the variance contribution is from larger SST features. Now, generating random fields using just the first and second order moments is insufficient, and this is seen by work by Asbalov in 2016. Here, 3 different random fields were generated using the same first and second order moments. However, as you can see from this bottom left plot here, the length scale of spatial continuity is much more pronounced to the east-west direction here. However, for the other 2 plots here, we can see a markedly different length scale of spatial continuity as seen here. Now, to address this issue, we're using a well-known concept in geostatistics known as the variogram or structure function, which basically serves to transfer the length scale of spatial continuity from our parent field to the random fields being generated. The structure function of variogram was generated for our initial parent field, and a theoretical variogram was fitted through it from which random fields will be generated, as seen in the next slide. Here's an example of 9 random fields generated using the same first and second order moment of our parent field, and in addition to this, the structure function as shown in the previous slide. The length scale of spatial continuity as seen here is 144 kilometers. We repeated the same workflow, but for a smaller length scale of spatial continuity of 72 kilometers, 36 kilometers, down until 6 kilometers. The next stage of our workflow will be to use this SST field with specified length scale of spatial coherence, analogous to the sizes of these eddies and filament type structures as boundary conditions for our uncoupled model run, to see how this affects the onset of the period of rapid intensification of model storms. To address this, we're going to be using an idealized model known as CM1 by George Bryan from NCAR. Now, this model has been used previously as a large eddy simulation mode, but in this case, we're going to be using it with a horizontal resolution of about 1 kilometer in the mesoscale mode. Now, we'll be running our experiment with 2 sizes of storms, one for a small size storm with an initial RMW of 36 kilometers, and another for a mid-sized storm of an initial RMW of 72 kilometers. And the aim would be to see how the sizes or the different sizes of storm responds to the spatial anomalies in sea surface temperature, particularly how this influences the onset of the period of rapid intensification. Initial results shows a plot of the maximum 10-meter wind speed versus integration time for a length scale of 144 kilometers. And this is shown for an initial small size storm of RMW 36 kilometers. Here we can see a spread in the onset of period of rapid intensification for different random fields with the same length scale of 144 kilometers. We ran the same simulations again, but for a smaller length scale of 72 kilometers, 36 kilometers, down onto a length scale of 6 kilometers. I want you to notice a spread, a different spread in this onset of the period of rapid intensification as we alter the length scale of spatial continuities in our random field. To visualize much more closely this variation in the onset of period of rapid intensification, we made a plot of these variances of the onset of rapid intensification against integration time. And we can see much clearly here that for smaller length scales of 9 and 18 kilometers, we have a lower variance, which kicks in much later, as you can see in these 80 hours, and stays progressively lower than those of the length scales of 36 and 72 kilometers as seen here. We made a plot of the variances of this 10-meter wind speed versus the length scales, and we can see much more clearly that the maximum variance is seen for the length scale of 72 kilometers, and for lower length scales, we have a minimal variances, and the same thing is seen here for larger length scales of about 144 kilometers here, suggesting an interesting feature going on for these length scales of 72 kilometers, which shall be investigated further. Now, for a mid-sized storm of 72 kilometers, we can see that this onset or these variances is not consistent here. This period of maximum variances is not seen here. Now, a plot of these variances versus length scale for a mid-sized storm of 72 kilometers shows a double peak, one for a length scale of 36 kilometers and another here for a length scale of 144 kilometers. To investigate the reason behind this maximum variance seen for a length scale of 72 kilometers, we took a look at the random fields used in generating these simulations. A closer look at these 2 simulations with widely spaced period of onset of rapid intensification basically suggests the dynamics responsible for the delay in the onset of rapid intensification for this simulation with this SST field. A closer look at the SST field used in generating these 2 simulations basically shows that the simulation with an initial rapid period or initial onset of rapid intensification corresponds to the simulation where the storm was initialized over a relatively warm SST anomaly of roughly 29 degrees Celsius. However, this simulation with a delayed period of rapid intensification corresponds to a storm initialized over a relatively cooler SST anomaly of roughly 28 degrees Celsius. A plot of the RMW against integration time basically shows something similar. We decided to take a closer look, but for a larger length scale of 144 kilometers, and this shows a similar result here. The simulation with an initial quick period of rapid intensification corresponds to a storm initialized over a relatively warm SST anomaly of roughly 29.5 degrees Celsius. And this simulation with a delay in the period of rapid intensification corresponds to a storm initialized over a relatively cold SST anomaly of roughly 28 degrees Celsius. And this suggests from the previous slides and this slide suggests that an SST anomaly of roughly 0.5 to 1 degrees Celsius is sufficient to lead to a delay in the period of rapid intensification ranging from about 20 to 40 hours. From this, we come to the following conclusion. A decrease in SST length scale leads to a decrease in the variance among the ensemble simulations for the small size storm of RMW 36 kilometers. The maximum variance for the small size storm occurs for simulations with length scale corresponding to about 2 times the size of the RMW. In this case, for the small size storm, the length scale of about 72 kilometers corresponds to that length scale where we saw the maximum peak there, the maximum variances. Now, the onset of rapid intensification is strongly modulated, as seen in this third point here, by the magnitude of SST anomalies as seen in the previous 2 slides. We saw here that SST anomalies of roughly 0.5 to 1 degree Celsius is just sufficient to lead to a delay in rapid intensification of about 20 to 40 hours. Thank you.